First of all, what are the things that we have done? Okay. So, we looked at the notion of a metric space. So, this was our basic structure that we studied in the previous part of the course. So, the metric space, we had a set, a non-empty set, and then we had a metric which satisfied the standard properties of a metric, which we all remember. So, that was the first starting point. Okay. Then in this we had several notions. First we studied the notions of the so-called topology, namely the open and closed sets. Then we looked at an important notion of convergence in a metric space. These were all consequences of the metric being there, and which in turn gave us the notion of Cauchy sequence idea, and these two together gave us the notion of a complete metric space. Okay. So, that complete metric space is one important notion that we had. Then we studied the notion of bounded sets and totally bounded sets. These were two important notions that we studied. Then we had compactness, sequential compactness, then we looked at the connection between all these notions. There are various theorems about how is the word compact connected with sequential to complete and total boundedness and so on and so forth. So, the connections between all these things. Then we also had studied the notion of separability. We did not study connectedness yet, but I thought I would postpone it. So, these are some of the basic ideas in metric spaces that we covered in our discussions in the previous part of the course. Okay. So, we will take on from here. So, when we looked at metric space, we started at a set X, which is non-empty, and that is all the only requirement on the set. We did not ask for any structure on the set X. So, for a metric space, we did not ask for any structure on the base set X or the carrier set X. All we needed was one non-empty set, that is all. No other structure was demanded. And secondly, we did not seek any special feature on the metric row. Okay. So, the two ingredients that go on to make a metric space are the base set X and the metric on that. We did not demand any special structure on the set X. We did not demand any special properties on the metric except the basic properties of the metric. So, now what we are going to do is, we now look for places where you have more structure on the set X and we have more special characteristics in the metric row. Okay. So now we look for, now we study situations where one, we have more structure on the base set X, and 2, row has some special features. The metric row has special features. Okay. So now we are going to specialize in the sense that, well, that is basic, but if we had something extra, why not use it? Okay. If the set X had little more structure, let's use it. If the metric had little more structure, let's use it. Then probably we should be able to get even more results. Okay. So what is the first in this? The first such situation one, the structure on the set X will be that it is a vector space. It is not just any arbitrary set, but it is a vector space. So X is a vector space over F, a field F, where we take F to be real or complex. We will take either a real vector space or a complex vector space. So now we are strengthening this fellow X is not just a set, he has more structure in him. So namely he is a vector space. And 2, I will first write the metric row arises in a particular manner. We will see what that particular manner is. Okay. Right. So let's look at this vector space, the base set X now. It is a vector space. So the typical model of the vector space that we know is our 3-dimensional space or the 2-dimensional plane. So these are our concrete models of vector space which suggests what we should be doing in a vector space. So if you look at the 3-dimensional or the 2-dimensional models that we have for vector spaces, one of the important things that we have for vectors is their length. This is what we are taught in school. A vector is something which has both magnitude and direction. Okay, some such funny definition we are given. So anyway, so the notion of a length. Okay, so therefore we now say we are going to go look for a vector space in which we can introduce the notion of a length. Okay, so what should be the length? The length is some number, is some kind of a quantification of that vector X. So therefore, so let X be a vector space over F, where again for me F is either the real numbers or the complex numbers. So let X be a vector space. Then we want to quantify each vector. That means with each vector we want to associate a number. So we want a function which takes vectors to numbers. So let n be a function from x vectors to the real numbers. We will take real numbers because our length, we want it to model the length. So now we will put all the requirements that we ask for a length. It should be such that 1, this quantification, if it were a length, we would like them to be positive. The length should be positive. Nx is greater than or equal to 0 for every x in x, and the length should become 0 if and only if x is the 0 vector of that vector space. I will denote it by theta x. X is the 0 vector of the vector space. Now, whenever we do something to a vector space, we should always worry as to what it does to the two fundamental operations in the vector space. The two fundamental operations are scalar multiplication and addition. So, what is the effect of this length over scalar multiplication? And we know that if we take a vector, we come back and see what do we observe in our normal life. We have a vector. If we multiply that vector by a positive number, the length gets multiplied by that positive number. If you multiply the vector by a negative number, the length gets multiplied by the negative of the negative number. So, it is the modulus. Therefore, we want this to be mod L alpha into n of x for every alpha in the field. This should happen even if the field is complex, and for every x in x. Okay. And of course, what does it do for the other operation x plus y? We know that if we have vector x and we have vector y, by the parallelogram law, the x plus y is the diagonal, and the length of the diagonal must be less than or equal to sum of the remaining two sides. That is the so-called, that is why the name triangle inequality, nx plus ny for every xy in x. Suppose n is such a quantification, then we will call n a length on the vector space or a norm on the vector space. So, then n is called a norm on x, and we write nx, instead of nx we write this symbol. From now on, the norm symbol will be the double line, norm x. Okay. So, norm x is greater than or equal to 0 for every x, 0 if and only if x is the 0 vector. Norm of alpha x is mod alpha times norm x, and norm of x plus y is less than or equal to norm of x plus y. So, okay, then x together with a norm is called a norm linear space. Normed linear space. I will from now on write only as NLS. Okay. Linear space means vector space is referred to as the linear space. It has now been normed. There is a notion of norm that has been introduced on that vector space, and that is called a normed linear space. We will see some examples, but before that, I hope the definition is clear. Okay. I will make one or two comments. We will have to connect it to what we have done already. So, the first remark is the following. So, consider a norm linear space. The operations, these operations are called linear operations. Okay, such operations like alpha acts linearly. Okay, alpha times x. So these are basically trying to say they behave like a line, right? You take a line in the plane, okay. If you add two vectors in the line, still they are in the line. Constant multiple of that is also in the line. The zero vector is on the line. Every vector has a negative or still on the line. So the line has been modeled. It will become a big space. Okay, it's a line-like space. Okay. Yeah.
Is it possible to have a vector space where you cannot define a norm? I mean,
Huh?
isn't it possible that we can define a norm always, and that all the time it is a norm linear?
We will look at it. I will come to that question. Okay. It is not a question of whether I can norm a vector space. The question is there are several norms that may be there. Which one is useful to us? Okay. Anyway, I will look at all those questions. So let me first make some simple remarks. Okay. Okay. Anyway, so now for xy in X, define rho xy. See, x is a vector, y is a vector, x minus y is also a vector, so the norm is defined. So define rho of xy to be x minus y. This is again modeled on our plane. I have vector x, I have vector y. The distance between them is precisely the vector, that length of the vector x minus y. Then this actually becomes a distance. Then rho satisfies all the requirements of a metric. Okay. So therefore of a metric on X. So we got hold of a metric. The moment we had a norm, it suggested a metric for us, and this is what I meant by saying that the metric rho arises in a particular manner. It arose from a norm. Okay. So we say, we call this the metric induced by the norm. There is a norm, that norm induces something called a distance between 2 points, and that's called the metric induced. So this is what we mean. We are going to have a vector space over F, and that has a norm, and the metric come from a norm. That is the special situation. So every norm linear space therefore automatically becomes a metric space because it is symmetric on it. So therefore every NLS is, so every NLS is a metric space with the metric induced by the norm. And therefore we can invoke all that we studied in a metric space into norm linear space. So can invoke all our studies in a metric space, simply import them into a norm linear space, because after all a norm linear space is also a metric space. So we can talk about open sets, we can talk about closed sets, we can talk about convergence, Cauchy sequences, completeness, boundedness, total boundedness, compactness, sequential compactness, all the notions with separability, everything can be simply brought into this structure. Okay. Yes.
Given norm,
You tell me. See, the metric comes from the norm. So already I have defined it. What is the question of uniqueness there? If this is the metric, the induced, if this is the norm, the induced matrix is this. This is defined to be this. This is called the induced metric. Okay. So which comes first? In a non-linear space, norm comes first, and the metric is automatically defined. There is no choice. There may be other metrics on X, but this is the metric induced by the norm. Okay. Each norm induces a metric. If you had a different norm on this metric space, then the corresponding metric that comes will be different. So each norm on the vector space makes it a new norm linear space, and the corresponding metric that comes out is different. It may happen that on X you may have a metric which does not come from a norm. So there are metrics on X which are induced by norms. There are metrics on X which are not induced by norms. That's a big question. Which metrics are normable? Okay, that's itself is a big question. Okay. So we have seen a lot of examples in metric spaces. We will see that many of them are going to be also nonlinear spaces. But therefore, examples are aplenty. Should I go through example? Okay, let me go through. Okay, let me introduce one or two notions and then we will look at the examples. Okay. The first notion that we can invoke, we are going to invoke. We can invoke all the notions that are there in a metric space into a nonlinear space. So we are first I will invoke the notion of convergence, because that's what everybody is interested in, approximations, etc., etc. So the first notion we shall look at is convergence. So I have a metric space, I have a nonlinear space. I have a sequence and X in X. We say Xn converges to X in this nonlinear space if, let's see what should happen. I know that this is a metric space and therefore I can talk convergence in terms of the metric. So what does the metric space convergence say? The distance between Xn and X must be made small, however small, sufficiently far away in the sequence. So the distance is defined in terms of the difference norm. So what it says is the norm between of Xn minus X can be made small. So if for every epsilon positive there exists a stage beyond which then the distance, that is Xn minus X, is less than epsilon. Then we say Xn converges to X in that nonlinear space. This is the, simply we are invoking the definitions we had in the metric space in the context of this special metric which has come from this norm. Okay, so in a metric space we saw that any convergent sequence must be Cauchy sequence, and therefore any sequence which converges in a nonlinear space must be a Cauchy sequence. So first of all, what is meant by a Cauchy sequence? Okay, so let us say this is the first notion of convergence. Then we have the notion of Cauchy sequence. Xn is a sequence in the nonlinear space is said to be a Cauchy sequence. Well, the same notion as the Cauchy sequence in a metric space, What is that notion? The members of the sequence are going to get clustered together as we go far off in the sequence. How do we say it? That we can make, you give me any small error, then there exists a stage such that if you go and look beyond that stage, any two fellows xn and xm, their distance is less than epsilon. That is what is meant by Cauchy sequence. Instead of rho xn xm, now we are writing norm xn minus xm. So exactly we are redoing metric spaces with the special metric where rho xy is norm x minus y. And because all these things we have seen in metric space, whatever holds there, every Cauchy sequence, every convergent sequence in a metric space is Cauchy, and therefore in a nonlinear space is Cauchy. Now in a metric space we saw that there may be situations where not all Cauchy sequences are convergent, and therefore we said that if all Cauchy sequences converge, we call it a complete metric space. So if all Cauchy sequences converge, we call it a complete nonlinear space, and complete nonlinear spaces are called Banach spaces. So if every Cauchy sequence in the nonlinear space converges, is called a complete nonlinear space or a Banach space. It was Banach probably had this idea. I mean, it was there floating around. Probably in some context he introduced this formal definition and called it B space. He was a little bit reluctant to call it Banach space, so he put his first name and called it B space, and people knew what he meant, so eventually said, okay, we'll call it Banach space. Okay. So Banach was one of the major contributors in analysis at that part of the time. Okay. I think the first 30 years in the 20th century, I think was the golden age of analysis. Okay. In a sense, a very real golden age of analysis, just like the second half of the 20th century was probably the golden age of probability theory. Okay. So now we will see some examples. Just like we can do why one is interested in Banach space basically it is rich enough to take care of convergent processes, approximations, etc. And when things are getting close, they are bound to get somewhere. Roughly that's what. So when you are doing some computations and things are getting closer and closer at every iteration, then they are getting somewhere, and what you are looking for. That's what essentially the idea is. Rich enough to do approximations and limiting processes. So any questions? Yes? Okay, so we will look at examples if there are no questions. I will first put in place most of the standard examples. Okay. So because whenever certain things are suspected that it might happen, one goes and checks in all the standard concrete cases whether it is true. And if it happens, it doesn't mean it is true. It's likely to be true. Okay, you need finally a proof. There are situations in at the time of Banach and all, there are certain things that are suspected to be true, maybe 50 years, because they were all true in all the concrete examples that we knew, but were shown to be not true in general 50 years later, okay, even though they were true in almost all the standard concrete examples that were known. One of such problems was the so-called Schroeder basis problems. Okay, anyway, so now let us look at some examples. Probably is the let me also make a comment here. The advantage of doing a norm-linear space is two things. Working in a norm-linear space are two things. One, it has vector space structure, so we can import linear algebra into it, right? And then all our knowledge and power of linear algebra into it. On the other hand, the metric brings in the notions of convergence, topology, and therefore analysis into it. So therefore, this is where algebra and analysis meet, linear algebra and analysis meet, and the power of both of them are invoked. Okay, the structure that we get out of linear algebra and the structure that the topological structure that we get out of analysis and the metric and the norm, these two, there is an intermarriage or whatever it is, and then we get results. Okay, that's when, if you want to do only linear algebra, or if you would want to do only analysis, probably you will be missing some of these results which come out of the interaction between analysis and algebra. That's the one of the most important things here. Okay, so therefore we will see something similar to linear algebra, but then pushed. Now we are able to handle infinite dimensional spaces a little better than just doing linear algebra. I'll point out some of those things. So the first example is, typically we know that we can take, let me put x to be Rn, where n is some fixed number. Okay, n is a positive integer, n can be 4 or 26 or 37. So let us take Rn, the n component vector space, and then we can define. I'll first write this, the usual length, which is square root of x1 squared, x2 squared plus xn squared, the usual Euclidean length, and that we know all satisfies. This is all these are the ones that motivated the definition of a norm, so they automatically satisfy. And then x with this, so Rn with this norm is a norm linear space. And what is the metric that is coming out of this norm is what we studied as the rho 2 metric. Remember that rho 2 metric, and the metric that comes out of this is the rho 2 xy, which is square root of mod xi minus yi squared summation I equal to 1 to n. This is what we call as the rho 2 metric. And this immediately suggests that we are having the rho p metrics, therefore we must be having the p norms also. So this norm linear space, since the metric space of these vectors with this matrix was denoted by L, what was it, L to NR. This 2 stands for this norm, right? R stands for all real components, N stands for the number of components, L is in honor of Lebesgue. Okay, that's the notation there. This NLF is denoted by this. So we are going to use the same notation as we used in metric spaces, because the metric that comes out of this norm, the metric that is induced by this norm, is the same as the rho 2 metric we saw before. And this immediately suggests that x equal to Rn with the p metric for for any p between 1 and infinity, this is a norm on Rn, and this metric space Rn on the metric induced is rho p xy is equal to summation I equal to 1 to n mod xi minus yi to the power of p to the power of 1 over p. In all these things, to verify that that's a norm, the only non-trivial thing is the triangle inequality. The triangle inequalities have all been proved, the so-called Minkowski inequalities and other inequalities we have already proved, they all follow from that. So therefore, I can denote this space by again L P N R. Okay, because this is the notation we use for the corresponding metric space. Since the metrics are the same, we will use the same notation. So what are the other examples that we know from this? Correspondingly, we have the infinite norm. Okay, so we have L N infinity R. What is this? X, in this case X is Rn, norm X is maximum of mod xj 1 less than equal to j less than equal to n, and the metric is maximum of 1 less than equal to j less than equal to n mod xj minus yj. So that's the next space. And then we can replace all the real components by complex components, then we get the complex norm linear. These are all real norm linear spaces. Everything is, all the vector spaces involved here are vector spaces over the real numbers. And now we can get correspondingly, so let me call this as 2 and this as 3, and the fourth example therefore will all be complex vectors, complex norm linear spaces. They will all be this L, N, 2, I will just put P, C, 1 less than equal to P less than equal to infinity, same types of norms. And the next generation of examples are remove the restriction that there are a finite number of components and take sequences. So the next example is LPR. What is LPR? For the X in this case is the set of all infinite sequences such that Xj belong to R, but such that summation j equal to 1 to infinity mod xj to the power of p is less than infinity. So let's take for 1 less than p less than infinity. Then what is a norm? It's simply j equal to 1 to infinity mod xj to the power of p to the power of 1 over p. Okay, now we have made sure that this is finite by taking only those vectors, and triangle inequality again has been proved for such sequences, and then the metric is the old metric j equal to 1 to infinity mod xj minus yj to the power of p to the power of 1 over p. Then we have not yet looked at the infinite case, so we next look at L infinity. I think I use my notation as odd. Is it the other way around? Where did I put the 2? Okay, this should be infinity and n, and okay, that's right. So this should be p and n, and this should be p, and now I look at L infinity R. What is this? In this case X is the set of all bounded sequences such that Xi belong to R and mod xi less than or equal to m. Okay, they are all bounded. For every sequence there is a constant m, that's mx. That constant may depend on the sequence. So bounded sequences. Then we define the norm x infinity as the least upper bound or the supremum of mod xj over all the j's, and the infinite metric is correspondingly the least upper bound of mod xj minus yj. Okay, so that's the L infinity space. Okay, and now the sixth example is replace R by C in 4, 5 and this should be 6, 4, 5 and 6, 4, 5 and 6, this is 7. Okay. Instead of real components you can take complex components. Okay, we have seen that all these are complete metric spaces, and therefore with this metric, and therefore these become complete non-linear spaces, and therefore these are all Banach spaces. Okay, so these are all Banach spaces. These are all complete with respect to the corresponding matrix, and hence or Banach space. Let me give you some examples. I will not prove certain things, I will just make some statements. Let me go give numbers. What is that? Number 8 is it? 7 is over. So let me give another example now. Let us take this example also I have seen. Let us take this notion. So x to be this. What is this? All continuous functions from the interval a b taking real values. So this is the set of all functions such that f maps ab to r and f continuous. So it is the set of all functions which map the interval ab to r, real valued continuous functions on the interval ab. Now 8a, on this I am going to define something called norm infinity, which is, because it is a continuous function on a closed bounded interval, it will have a maximum and a minimum. So in particular mod f will be continuous and therefore it will have a maximum and a minimum. So we call it as maximum of mod fx as x varies over a. This maximum exists and therefore that is well defined, and this is a norm. Okay, and the corresponding infinite metric is what do you call it? Maximum of mod fx minus gx x belong to. And when you talk about convergence in this metric, it boils down to uniform convergence of sequence. When you talk about a sequence of functions which converge in this metric, it boils down to that sequence converges uniformly. And similarly, when you say it's a Cauchy sequence in this metric, you mean they are uniformly convergent, uniformly Cauchy. And a uniformly convergent sequence of continuous functions will converge to a continuous function, and if a sequence is continuous and uniformly Cauchy, it will converge to a continuous function, and therefore that will be a complete metric space, and that will be a Banach space. Okay, so this is a Banach space. Now I will make a few statements only. I will not prove them for the time being. You need some more ideas to prove it completely. Many more ideas to prove it completely. So now let me keep the same x, namely the vector space of continuous functions. The continuous function from a vector space, because sum of two continuous functions is a continuous function, constant multiple of a continuous function is continuous, every continuous function there is a zero continuous function, every function has a negative continuous function, and so on and so forth. So that is automatically a vector space. I am going to retain the same vector space, but I am going to now introduce a new notion of length, another notion of length. So what I looked at here was the peak that the function would reach, the modulus of fx, the peak both ways, up or down. Okay, what is the maximum it will go up or down? Now that looks like not a good measure of the function in a sense. Okay, you are ignoring all other fellows what they are doing. So what I will do is take some kind of an average. Okay, so let us say first I will now define to be the averaging process in continuum is the integration. Integration is an averaging process. So I will define A to be mod ft dt, and this is a norm that can be verified. Okay, that's not a that's a simple exercise in calculus. So and properties of continuous functions, and therefore that's a norm, and the corresponding metric is equal to A to B mod ft minus gt dt. And if you use this norm, the same vector space, but now a different notion of norm. With this norm, this is not a Banach space. Okay, so this space is not Banach. So CRAB with this one norm is not a Banach space. So what it means is there are two independent ingredients, namely the vector space and the norm. Each has a role to play and each has a say in what the structure is. Okay, you may say I am the same vector space. I don't care, I change your notion now. Length looks different and you are no longer a Banach space. You are not rich. We have made you poor. Okay, it's not rich enough to do convergence. So in the convergence world, this becomes poor. Okay. Now instead of the one average, you can take the P average. So the next one is, in general, you can look at norm Fp to be A to B mod ft dt to the power of p to the power of 1 over p, and the p metric is this A to B mod ft minus gt to the power of p dt to the power of 1 over 2. You can take any p between 1 and infinity, and that's not a Banach space. For all these p's, this is not a Banach space. Not a Banach space. So therefore, in a sense, continuous functions are not rich enough from averaging point of view. Okay, continuous functions are not rich in that sense. Now, when somebody is not rich, you go and make him rich. Give him more money. How much more I have to give him to make him rich? So in other words, when some space is not complete, what does it mean to say that it is not a Banach space? It is not complete. So whenever you have an incomplete metric space, there is a process of completing it. Okay, and this completing process is done in the most efficient way. In other words, just the optimal completion. You don't give him too much money also, just that money required to make him to be classified as rich. Even 1 rupee more is not given. Okay, if you want to be classified as a crorepati, you need crores. I don't give you 1 crore 1 rupee also, I give you only 1 crore. If you had 99 lakhs, I will give you 1 more lakh, that's all. So the optimal complete, the way of making it, that's called the completion, and therefore every one of these incomplete metric spaces can be completed. And what we get are the famous Lebesgue spaces in the context of Lebesgue integrals and Lebesgue measure, the capital L1, the capital L2 and the capital LP spaces, okay, correspondingly to this little L1, little L2, little LP spaces. We have the capital L1, capital LP. So we will get the corresponding completion here will be called L1AB, or of course here it will be called LPAB. These are no longer continuous functions, these are what are known as Lebesgue Pth power integrable functions. Okay. Well, that is what Lebesgue measure and integration. In general, you can go to general measure and general integration and get the LP spaces over a measure space, okay, with respect to a certain measure. So that is the beginning. In fact, the way the 20th century began was with Lebesgue's thesis, in which he proposed the formal notion of measure, Lebesgue measure on Rn, and introduced what is meant by measurable functions, and then what is meant by integration, which is a generalization of what Riemann had done about integrations, which brought in functions which are not continuous into the fold of analysis, proper analysis, and that was the starting point, I think, for the golden age of analysis in the first 30-40 years of the 20th century. Okay. So that's part is a course on Lebesgue integration. Okay, that part, this completion, etc., etc. Right. So these are some of the examples. Now, since we say that this nonlinear space is a business between linear algebra on one side and analysis on the other side, we have seen the business of linear algebra coming in through those vectors, vector spaces, various vector spaces we saw, and the business of analysis coming through convergence, continuous functions, etc., etc. But then again, let's go back to linear algebra. We always deal with matrices. Okay, so let us look at these matrices first, and then later we will see how does that get carried over when you are analyzing a nonlinear space. What is its place? The role of linear algebra, matrix in linear algebra, if it had to be carried over to this nonlinear space situation where there is an additional analysis also, what is the notion that we get? So before that, therefore, we look at a nonlinear space which involves matrices themselves. Okay. So my next example, or last example for today, is the following. I lost track of the number, so 9. This is the first time I completely kept track of the numbers. 9, let me first take X to be the vector space of all m by n real matrices, where m and n are fixed. Okay? Take a fixed m and n, take all m by n real matrices. Okay? We know it's a vector space because sum of 2 m by n matrix and m by n matrix. The 0 is associative, 0 matrix is there, every matrix is a negative matrix, you can multiply a matrix by a scalar and it is still an m by n matrix, and so on and so forth. So my vector space is the vector space of all m by n real matrix, so it's a real linear space. Now I am going to introduce a norm. So how I introduce, I already discussed this in the metric space class, but again I will go through this. So what do we want for a norm? Given a matrix, we must associate a number with it. Okay. So I am going to look at, so consider a matrix A, A11, A12, A1n, the ith row is AI1, AI2, AIN, and then AM1, AM2, AMN. So the matrix has m rows and n columns, and all the entries are real numbers. Now what I do is, I take the first row, take the magnitude of each entry and add them. So in other words, the row sum, first row sum, but with all the terms with an absolute value. So let me call it as row 1. Row 1 to be sum A11 plus A1n. And this I do for each row. What is the ith row sum? Let me now write that. Is AI1 plus AI2 plus AIN, but with all the absolutes. So I will write it as summation j equal to 1 to n mod Aij. I is fixed. It is the column index that varies. So mod Aij from j equal to 1 to n. So I do this for each column, each row. Okay. How many row sums do I get? I get m of them. I look at the maximum of them. So I will call row of the as, I will, let me call it as R, so that it comes from row sums. I will remember that. Okay, is the maximum of row 1, row 2, row m. Actually I should call this as row 1A, row 2A, row 3A, and the maximum of all this y depends on A. Okay. Okay, why is this a norm? Well, certainly it is the maximum of non-negative quantities, it is non-negative. If this were 0, each one of them will be 0. If this is 0, all the entries are 0. Therefore, the matrix must be 0 matrix, and triangular inequality similarly followed. So, therefore, this is a norm. Okay. So, this X norm R is a non-linear space. And what is the metric that we get out of this? The metric is the distance between two such matrices, that will be the maximum of row 1 A minus B, row 2 A minus B, row M A minus B. Okay. Now I will just make a comment which I will later look at it in more detail and justify it also. We have vector spaces on the one hand, we have the norm that is going to come and interact with it. The main thing that the norm is bringing in is the notion of convergence, or all the ideas that come from metric. The most important thing that we are interested in the metric topology that is coming is the convergence. We will see all others are coming out of that only. One way is look through open sets, the other way is through convergence and then closed sets and then open sets. So you can look at it either way. So the important ingredient that the norm supplies is the metric, which in turn supplies the notion of convergence. So each norm introduces a notion of convergence. Okay. Each norm induces a metric, and each metric induces a notion of convergence. It turns out, if you have a finite dimensional vector space, you start with any norm and look at the metric that comes out of it, that will give a convergence. If something converges in one norm, it will converge in all norms. So in other words, there is a total collapse of the distinction as far as the topology is concerned, coming out of the various norms in a finite dimensional space. So in other words, what it says in finite dimensional spaces, there is essentially only one notion of convergence, norm convergence. Okay. This is basically about, there is nothing interesting in finite dimensional vector space. For an analyst, that isn't much interesting in finite dimensional vector space. What is the other studying? You put one norm and study everything. There the story ends. And I know a very simple norm. Any finite dimensional space is isomorphic to Rn, and Rn I have the usual Euclidean norm. I am done. That's all. You are not doing anything great. So when you are doing finite dimensional analysis, you aren't doing anything great. Okay. You may do a lot of computational methods, numerical analysis, etc., etc. But then as analysis, nothing great comes out. So the interesting things in functional analysis in study of nonlinear spaces come out when you are dealing with nonlinear spaces in which the base vector space X is infinite dimensional. And that is the only thing which we struggle when we study linear algebra. The question of basis is a terrible problem when you are studying linear algebra without analysis. When you are dealing with infinite dimensional spaces, the basis could become very large, the so-called Hamel basis, in fact so large that it is useless, and therefore analysis has to bring some semblance of sense into all these things, and we will see how it comes. Sometimes fails, sometimes works, and so on and so forth. So basically the interesting things will be the infinite dimensional spaces, of which this is an example, this is an example, these are all examples of infinite dimensional nonlinear spaces, of which this is a infinite dimensional Banach space, and these are all only infinite dimensional nonlinear spaces which are not Banach spaces. Okay. So what I will do next time is jump a little bit and say what we should be. I have linear algebra, I have Banach space and nonlinear space. In linear algebra, the matrix theory plays the important role. There must be something corresponding here which plays important roles. What is that? How should we get to that? Okay. And in other words, we will look at what is it that matrix, why is it that the matrix so important in the analysis of linear algebra? So therefore, what should we look for here? Okay. So this leads us to the notion of, just like we have the space of matrices, we have the so-called notion of bounded linear transformations on a nonlinear space. And just like we have the so-called functionals in a metric, in a vector space, linear algebra, there is the notion of bounded linear functionals on the, these are the two fellows who basically tell us a lot about these nonlinear spaces, just like a matrix plays an important role in the analysis of geometry in a vector space. Okay. So therefore, what I will do is I will be doing a bit of non-standard crisscrossing. Okay. So I will jump to the equivalent quote unquote role of matrices in linear algebra to linear transformations in vector spaces, in nonlinear spaces. So that is what I will take up next. So from next time onwards we will meet here 5 to 6, Monday and Wednesday.